Hi guys, it's Kate. This video is about optimization problems, how to identify them, how they work, tips and techniques for solving them in a nice and organized and relatively stress-free fashion, and then a few practice problems to follow. Right off the bat, you want to be clear about how to identify a problem is known as a quote-unquote optimization problem. And you can do that by honing in on some of the key words that are frequently used in these problems. Largest, smallest, cheapest, most expensive, greatest, least, longest, shortest. All these words cue you to start thinking about how to maximize or minimize some quantity. And that's what optimization is really talking about. Now, what people really don't like about optimization problems is that they're dense. There's a lot of information in these word problems. And one of the most important things that you can do is understand from a top-level perspective what it is that you're trying to do. And in this video, where we're going to be doing some optimization problems and talking about some techniques, I'm going to refer to the process of solving an optimization problem as breaking down into 3 separate steps. The first step is to build a function that models the quantity we are maximizing or minimizing. This involves a lot of work and a lot of focus on detail. We'll be talking about tips on how to do that effectively and well. The second step is to analyze the function to identify the desired max or min that you're looking for. Then the third step, which is so often forgotten, is to make sure that once you've analyzed the function, found that max or min, make sure that you use that information to then go back and answer the original question that you've been asked. Now, what's very challenging about these problems is that they're dense, right? They're long to read, they're hard to make sense of, and I want to value each of these 3 parts. This is how we're going to work through these problems every single time, and consistency is what you want to strive for. So the techniques that you're going to be seeing here are first, readings and rereadings. You should not expect to get all the information for the problem at the first reading at the top of the problem. It's one of the most common errors that students make, and these rereadings again and again at strategic moments throughout our process are going to be done in a way where we're filtering for particular types of information. The second piece is clarity in terms of our objectives and goals. Even going so far as to write down in a complete English sentence what it is that we're trying to do. This way, if something goes wrong and we get a nonsense answer at some stage of the problem-solving process, we can go back and look and see, at this point I was trying to do this. Does the mathematics underneath that actually do what I said I wanted it to do? It gives us a good framework with which to work through these problems. And one of the other things that we're going to do is also to continuously attempt to tie these functions, which can get really bogged down in mathematical notation and derivative speak and concavity discussions, really trying to tie them back to the practical, real-world quantities that you designed them to model in the first place. And 2 other techniques that I very truly endorse and am pretty annoyingly adherent to are writing from left to right and top to bottom. I can't stress it enough. I don't mind sort of quirky layouts and things of that nature, but some of the pieces of paper that come across my desk or across my computer screen have information written absolutely everywhere. It's hard for the grader, but more importantly, when you're in the thick of it, you want your work to be organized and focused for you to navigate so that you're clear on where you are in the process, how far you have to go, and what your results are telling you. So find a layout that works for you. Yes, you must write left to right and top to bottom, but use that layout every single time. It will decrease the number of variables you're dealing with when you get into a test-taking setting. The question is already going to be different. Don't make everything else different as well. Now, Before we dive right in, I want to talk about these 3 steps and what they're going to look like. When we're first given a problem, it's going to be a dense amount of text, and it's going to have an ask within the problem, like a question that it's asking you, right? It's asking you to find the cheapest box that does the following things, etc. That piece of information is going to help you identify what it is that you're maximizing and minimizing. When you go about doing step 1, you're going to go from not very much detail to all of the information you have in the problem within that function. Don't try and push it and create the function right off the bat. First, we're going to start with a mathematical relationship, and then we're going to add more and more notation and more information from the problem until we get to a function of 1 variable. So in number 1, when you're building a function, you may start with a looser equation that has lots of different variables, and then it will transform itself into a function of 1 variable. The other piece of information that you really need to determine is, okay, you've built this function. Which part of this function really matters to you? When we work on projectile motion, we frequently use parabolas. The pieces of information given to us usually tell us our initial height, which is the y value at t equals 0, and the initial velocity, which tells us whether the object is being thrown up, thrown down, or simply released. And what's interesting is that even though this parabola has an unlimited domain, for the purposes of this type of problem, where you're modeling a physical activity such as throwing an object that begins at some given t equals 0, you only care about 1 piece of it. From the moment it is launched out of the window to the moment that it hits the ground. This is what we talk about when, as we're building a function, we're trying to figure out what the domain is. What are the possible values for the input that are actually relevant to the physical relationship we're trying to describe, whether that's volume or cost, etc., etc. But this idea of taking a model that is actually an unlimited domain and restricting the domain to simply just a piece that we care about, where just this piece models the trajectory of something you've thrown out the window, that is what we're doing in terms of a domain. Yes, we'll have this model that may not have a restricted domain, but only a piece of it will be relevant to the particular relationships that we're describing. You cannot move on to number 2 very well until you've mastered number 1. But once you've mastered number 1, you'll move on to number 2, analyzing the function to identify the desired max or min. And that's where it's really important to do the same thing every time, very systematically. We're going to talk about some of the different techniques that you can use, the tests, first derivative test, second derivative test, etc., etc. And then we'll be answering the original question. Usually when I speak with students, they feel pretty confident about 2 and 3. It's really number 1 that is the issue, building that function that models the quantity we're maximizing or minimizing. Let's start looking at how to use this framework to work through optimization problems, using our strategic reading and rereading, our clarity and our objectives, and connecting the mathematics to the real world with organized work that is the same format every single time. What I'll be looking at is worksheet 27 here. This is the optimization worksheet from the first day of class where we reviewed optimization, and it has a lot of good questions on it. So let's apply this framework to those problems. This problem is an extension of a problem that you may have covered in a previous class, but regardless of whether you did or not, there's a soda can company and they're building aluminum cans. And they realize they need to use stronger aluminum for the tops and bottoms of the cans, and this stronger aluminum costs 3 times as much per square inch as the aluminum used for the sides. If the company wants to minimize the cost of each can, what dimensions should their cans be? And it says, remember, the volume of the can is 128 pi cubic centimeters. Now, the first tip I have for you is when you're reading a problem like this, don't put your pencil to paper at the end of it. Just read it over once so that you can identify it as an optimization problem, and that's it. That's all you should do upon the first reading. And if there's a part A, a part B, a part C, which does not exist here, but may on an examination, read through those as well. See what the direction of the problem is before you begin. This is just to give you a lay of the land. So here I can definitely identify it as an optimization problem. And why is that? Well, I can see this if the company wants to minimize the cost of each can. Preface. It's that moment right there that says to me, this is an optimization problem. So upon first reading, don't write down a single thing. Just read it, get a sense of what's happening, and whether or not it's an optimization problem. All right, now that we got that out of the way, you want to do a second reading. In this second reading, you're going to zoom in, you're filtering just for the information that will tell you what it is you're looking to maximize or minimize. Take a moment and identify that in this problem. All right, as we move on, note that everything I put in gray is not something I would actually write on a piece of paper. There are more directions for us. These are the tips and techniques I was talking about. So what quantity are we going to maximize or minimize here? Well, it tells us right in that highlighted sentence, the company wants to minimize cost. And using our other technique, being explicit about our goals, I'm going to write that down as the first thing that I would put on my piece of paper. Now, the minimizing is going to come much later. That's in the second part of our three-step layout. That first part is that we need to find a function that models cost. And as I mentioned before, one of the pitfalls is that students really want to jump straight to writing down a function of one variable. But in general, what you want to do is try to go from a rough outline of what about this can costs money, and then get more specific with more and more readings of the problem. So the pieces of the can that cost money are the top and the bottom and the sides, and I can see that from how this is presented to me in the beginning of the problem, where the cost comes from aluminum, that there's strong aluminum on the top and bottom, and that there's weaker aluminum on the sides. But just to start out with, as a general equation, the total cost is going to be the cost of the top plus the cost of the bottom plus the cost of the sides. I'm now going to do another reading of this prompt, and I'm looking specifically for information about the various costs. And as I mentioned just a moment ago, it says that the stronger aluminum costs 3 times as much per square inch that's being used for the top and the bottom as the sides. We're also noticing that the rate of aluminum, the cost of aluminum, is some price per square inch. Square inch is a unit for area. And so what that means for the purposes of our problem is that when we go about including more information about our total cost equation, that means cost is going to be very closely related to surface area, the physical property of the can that's measured in those square inches. So we are going to be working closely with surface area, but it's not going to be exactly like surface area to give us the total cost function. And we also want to notice that we need to incorporate this stronger aluminum costs 3 times as much on the top and bottom as it does on the sides. Now, if I were just trying to calculate either of these 3 individual costs, I would take the surface area of the top times the cost of the aluminum being used for the top, which would be C sub T, cost of top is what I'm trying to say. So you'd effectively have surface area, which is square inches, times cost, which is dollars per square inches, and you'll be left with the total dollars that the top costs. You would do the same thing for the bottom and the same thing for the sides. Now, we had noticed in our rereading as well that cost for the top and the bottom, both of these, CT and CB, are 3 times the cost for the sides, so I'm going to incorporate that information in now. Note that we have a common factor in each of these terms. Each of these terms is being multiplied by the cost of the sides. Yes, the surface area of the top and the surface area of the bottom are both being multiplied by 3 times the cost of the sides, but we can still factor out that cost of the sides. And you may be wondering, why did I do that? Well, the reason is that I can just divide out the cost of the sides. The cost of the sides is some price per square inch. It's essentially acting as a scalar multiple for this function inside here, which will definitely involve variables because we get to choose our radius and our height, which we're going to get into in just a moment. And what's important to realize is that you can multiply a function by any scalar multiple as long as it's positive, and this will be because it's a cost, and it will still have its maxima and minima in the same place, right? Multiplying by a scalar will just vertically stretch the function. What's really causing the maxima and minima is in here, not out here. So I'm going to divide out the CS, and I'm going to say the total cost is 3 times the surface area of the top plus 3 times the surface area of the bottom plus the surface area of the sides. Here's where a picture of that can would be really helpful. Draw a cylinder, label the important parts of a cylinder that are involved in the computation of its surface area. So that would be radius and height. Now let's start to get some formulas in here involving radius and height instead of surface area top, surface area bottom, surface area sides. Now the top and bottom are circles of radius r, so their area is simply pi r squared. Let's put that in. The surface area of the sides is a bit more challenging. If you were going to look at the surface area of a can, you would take that side piece and slice it down the front and unroll it, and you would get a rectangle. Now the area of that rectangle is its length times its width, and one side of that rectangle comes from the height of that cylinder, but the other side of that rectangle is certainly not the diameter there. This rectangle went all the way around the can, so it comes from the circumference of the cylinder there. And circumference is equal to 2 pi r. And so this area is going to be 2 pi r, which is going to be the length of that rectangle, times h, which is the width of that rectangle. Now we have an equation for cost that involves multiple variables. We're not quite there, and that's okay. We now need to get it in terms of one variable, because there are so many r's and so many h's, and we really need to just pick r or h. So this is the moment where we do a third reading of the problem. Going back to that tip that I was talking about, rereading, filtering for particular information. We want to filter this time for additional information that restricts the variables, meaning that the radius and the height of this can can't be whatever we want them to be. And as you read through, note that anything we've used already probably isn't going to be what restricts the variables. So this conversation up here about the stronger aluminum is not what we're looking for. We used that in our cost function. It takes until the last sentence before we find information that we have not yet used. And it's that volume of the can is 128 pi cubic centimeters. All right. I put that in for filter for information that restricts and relates the variables, and what we honed in on is that the volume of the can is 128 pi cubic centimeters. Now this is like a mess of a problem that definitely didn't make it by a copy editor. So I'm going to change one thing about it, like as the person in charge of this walkthrough, you would not see this happening on an exam question. You would not be put in a position where you would need to do this on an exam question. And if you feel like you are, you should always raise your hand. But the area units need to match the volume units because we're using radius to compute area in the cost expression up here, and we're about to use the same radius and height in a computation for volume, which would be equal to cubic centimeters. So we can't have like radius and height be somehow equivalent to inches in one space and then equivalent to cubic centimeters in another. So I'm just going to go with cubic inches everywhere. You're welcome. So let's continue with this. We have filtered for information that restricts and relates the variables. Basically information that says, hey, radius and height can't be whatever you want it to be. For us, that is that volume is equal to 128 pi. And volume can also be computed with a formula for using radius and height. And whenever you have a prism, this is a prism whose base is a circle, right? the equation for the volume is the area of the base, which would be that circle, times the height. So for us, this also implies that pi r squared, the area of the base of the cylinder, times its height is equal to 128 pi. And this is really important. This piece is really important. I probably should have squared that in gray. And I'm also going to circle where we left off in terms of creating our cost function. Because the whole purpose of finding this information, which related radius and height to each other, was to try to get this initial equation that still had two different variables in it in terms of one variable. And this statement about volume will allow us to do that, because we'll be able to take h and express it in terms of r, or r and express it in terms of h, and then take that information and plug it in for either r or h respectively into the equation that has two variables, and it will transform into a function of one variable. Now the question becomes here, when you look at your original equation, what would you rather plug in for? Do you want to plug in one thing for one appearance of h, or do you want to solve for r and then plug it in here and square it, and here and square it, and here? You want to choose the path that involves the least amount of work. And even though you can absolutely solve for r squared and have a pretty reasonable substitution here and here, it gets a little messy here, and it's just a lot of work. If you're subbing in for r, you definitely want to sub in for h instead. So what we're going to do is, in this piece of information, we're going to solve for h and put it right back in here. I want to take a moment to call out a common mistake that's made in this step. Be very clear with what you're doing through these first two steps. This equation up here that is modeling cost that will ultimately turn into a function of one variable, this is the quantity you're seeking to optimize. This equation down here, which involves the same variables that you see up here, certainly on purpose, but discusses how they're restricted, is what we're going to call the constraint. You want to call this your function. Here it's a function of two variables, but it's still a function. Here we'll call it a function. This is the constraint. They're two different things. You do see the same cast of characters, but note that here what is outputted is the thing that you're trying to maximize or minimize. And here, whatever you plug in for r squared and h has to equal 128 pi. That is a volume calculation. The difference is enormous. Note that so far up here, if I didn't tell you anything else, the implication is you could plug in anything for radius, literally any real number, which is not the case, but we'll get to that in just a moment, anything for radius and anything for height, and it would spit out what the cost of that particular can would be. Down here, this is telling you, hey, if you plugged something in for radius, it's telling you exactly what height would need to be, because the left-hand side has to equal 128 pi. The constraint is saying, hey, the volume has to be this. The function is saying, ooh, if radius and height are these two values, here's what the cost would be. It is an input-output relationship. So often I see people taking this piece of information, how the variables relate to each other, and plugging it back into itself, into the constraint. And so there's a circularity. If I plugged in 128 over r squared right here, you would just get 128 pi equals 128 pi, because this relationship between height and radius itself came from this above line. You want to take this statement, which comes from the constraint, and incorporate it into the function. That is going to update the function to accurately reflect all of the information that's being given to you in the problem. Now down here, here's my function of one variable. I took 3 pi r squared plus 3 pi r squared, and I restated that as 6 pi r squared. I have 2 pi r times 128 over r squared. This can definitely involve some algebraic simplification, and so I'm going to rewrite it, and I'm also going to rewrite it using negative exponents instead of expressing things as fractions. Now, the last thing that will happen before we close out of step one, which is we built a function that reflects all the information in the problem, is that we need to think realistically, which values for r do we actually care about? This function, this 6 pi r squared plus 256 pi r to the negative 1 power, is defined for a lot of values of r when this is taken out of context. Meaning if you were just given this function outside of this problem, you would say, oh yeah, I could totally plug in negative values of r into this, which is absolutely true. But similar to what we discussed on the first page, when we're looking at a parabola that models projectile motion, we only care about a piece of the parabola that corresponds to the trajectory of the particular object we're talking about. Similar to this one, this function has a very large domain, basically everything except for r equals 0. But not all of those values of r actually correspond to a real, practical, physical representation of the relationships that we see in this problem. So before we move on, the last thing you need to do to get your function in order is to figure out what values can r take on. Well, a radius cannot take on negative values. We don't measure radii in terms of a negative number of inches. So that means that r's minimum, according to this problem, is 0. That's not achievable because the second that r is 0, that means the can ceases to exist. And then you want to think to yourself, okay, there may be a maximum that r can take on. Is that true? Well, if we look back here both at this can and both at what this relationship is telling us, that h equals 128 over r squared, that means that height is in tension with r, right? Height, the product, some product of height and radius squared and pi, compute volume, and we need that volume to be 128 pi. And so if radius is really, really small, in order to hit that 128 pi cubic inches, we need height to be very, very large. If height were very, very small, radius would need to be very, very large for us to hit that 128 pi. Now, what's interesting is to think, okay, I understand that radius at its smallest, right, will be 0, but not inclusive of 0. That means that radius at its largest will be when height is at its smallest. So the question becomes, does height also have a minimum, or is it similar to radius, which is that it doesn't actually achieve a particular minimum? And the answer here is, hey, there's this interesting algebraic relationship here. If radius gets really, really large down here in the denominator, really, really big, is there any ceiling on how big radius can be? Well, theoretically speaking, when we're looking at this relationship, the answer is no. H will still be positive. It won't have leapt over into the negative space. Radius could be huge. It just means that H is going to be really, really, really close to 0 in order for that 128 pi requirement to be met. So radius can be as big as you like. It's a totally impractical can. It's definitely not something you'd see on the shelves with a huge, huge radius. But height is going to shrink down to 0 in order to balance it out. And so there is no maximum radius that can be achieved. It's just going to go to positive infinity. And that moment where radius grows without bound is where height is the same time that height is going towards 0. And I've drawn two comically ridiculous cans that sort of represent, not drawn to scale because it would be really, really tall, but those are the ideas of what's happening at either end of this interval for the domain. So what the domain is really asking when you're restricting the domain, saying which part of this function do I care about, you're saying now I'm bringing it from a function out of context. Like if I was just looking at C of r equals 6 pi r squared plus 256 pi over r, I would be like, okay, out of context, the only value r can't be is 0. But in this particular problem, r definitely has to be positive. We do not care about r assuming negative values. That has no analog in this problem. You can't have a negative radius. And also r is not going to have a ceiling. We're just going to let r take on any of the positive values that are allowed. There's no additional information in this problem that would indicate that that's impossible. The only information that we have is that this relationship needs to be true, and r growing without bound does not make h jump out of a reasonable range of heights. It will be a silly height. It will be ridiculously small, but we're pretty much thinking that that's not going to be there because both of these cans, the one that's extraordinarily tall with the teeny tiny radius seems really, really expensive because it's going to be so tall. This one here, which is huge radius, tiny height, is going to be so expensive because the top and the bottom, the two expensive parts of the can, are the biggest. So both of these, neither of these seem like the way to save money. But this is going to be our domain, and we expect to land somewhere in the middle to find our minimum of cost. Now, the reason that I wrote this function this way is because it's much easier to take the derivative with the exponents written as negative numbers instead of as fractions. So we're now moved into phase 2 of analyzing this function on the particular domain. Take a moment, write down the derivative. And we also definitely want to set it equal to 0. This is how we are going to locate the critical points of this particular function. Solve for r, and a good tip for this is to translate back into expressing these moments where r has a negative exponent on it as a rational expression, so a numerator-denominator situation. Then the algebra is much more straightforward. All right, we found a single critical point. You could have also expressed this as the cube root of 256 over 12. As our last step in our analysis, we want to double check that this is in fact a minimum in the cost function. And this particular moment has a fork in the road. You can either do the first derivative test, or you can do the second derivative test. This expression right here is a great candidate for the second derivative test because it doesn't look like sine will be very challenging for us to determine out of the second derivative test. Because in the second derivative test, all we need to say is at the critical point, is the second derivative positive, in which case it's concave up and therefore a min, or negative, in which case it's concave down and therefore a max. We already suspect, because of the two sort of ridiculous all height and almost no radius and all radius and almost no height, that those are the expensive approaches towards the endpoints. And so the critical point we found in the middle is probably going to be a minimum, or at least we hope so, because this entire problem is talking about it. But let's apply the second derivative test to this first derivative. Sure enough, when we take a look at the sign of the second derivative over the restricted domain that we have constructed here, if we plug in a positive value for r, this entire thing will be positive, meaning that the second derivative is concave up at our critical point, because our critical point is where r is positive, meaning we are at a minimum. So I've written down my second derivative test. I've said the critical point is a minimum. That's great. We now have a fourth rereading of the question right at this moment to check for stage 3. Have we actually answered the question? I go back up to the top of the page and it says, if the company wants to minimize the cost of each can, what dimensions should their cans be? Well, the two physical quantities that you can measure are radius and height. I haven't quite gotten there. I have radius, so that's good, but I do need height if I'm looking for dimensions. I'm going to go back to this moment right here to quickly find the height, and then I'll be done with the problem. Here's the computation. And now we're done. Take a look back. Notice all of the rereadings we had, the layout of the problem. Here in the center, we started with a general equation for cost. We tied it correctly to surface area. We found a function first of two variables, used additional information to find a constraint on those variables, updated that original function with that information to get into a function of one variable, thought through the values for radius which would be relevant to our function to restrict the domain accordingly. Neither of the endpoints were included, so we were only looking on the interior of the interval in order to find critical points. Applied the first derivative test to do that, found one, applied the second derivative test to classify it as a minimum, and then reread the problem one last time in order to make sure that we had found the complete solution and not just done this and left us hanging in terms of actually finding the dimensions. I'll be posting a couple more videos with some practice problems as well. Feel free to email if you have any questions.